Hello, this is Emad Mirabi. I want to teach a bit of chemistry A level. I want to teach a bit of this book, which is the exam board is OCR. Okay, so I chose a section in chapter 23, redox and electrode potential, to teach. Here in chapter 23, section 4, we have electrode potentials. It is on page 386. Okay, let's go to this section. In this section, we have a table here. This table is a standard electrode potentials, okay, or also called standard reduction potentials. It is just like the reactivity series of metals that the students have learned previously in 9th grade. So the upper species they're more willing to lose electron. For example, magnesium is a very reactive metal, so it wants to lose electron vigorously. And then aluminium is the same thing. And then coming down, we will face hydrogen and then copper here, or elements like silver, which are not very much willing to lose electrons. So the higher in the table we go, the upper we go in the table, the species is more willing to lose electron or get oxidized, or is a stronger reducing agent. And down this table we go, the species are less willing to lose electron. They're more willing to gain electron, so they are good in reduction, so they are strong oxidizing agents. So let me write this in another form. Okay, here is, so we said the trend is like this. The trend is like this. If we go up, they're more willing to, the species are more willing to lose electron, or they are more willing to be oxidized. Or we can say they are greater reducing agents, because if a species gets oxidized, it loses electron, and that electron will reduce other species. So they are greater reducing agents. Okay, and down this table we go, it is vice versa. So they are greater oxidizing agents, or they are more willing to be reduced. Okay, so now based on this information, let's work on some questions at the end of this section. The question at the end of this section, for example, let's do question number 4, or part of question number 4. Here is the question. It says, refer to table 1, which is the same table. Calculate the standard cell potential for the following cell from the redox reaction in table 1. Okay, so here we have copper, and here we have chlorine. Where is copper? Copper is here, and chlorine is here. So in comparison between chlorine and copper, definitely copper loses electron and chlorine will take the electron. So copper oxidizes and will be the anode electrode, and chlorine will gain electron and it will be a cathode electrode. So let me write. So to answer part AI of this question, the question says calculate the standard cell potential. Okay, let me write because in part B it says for each cell given in part A, write half reaction for the oxidation and reduction. So okay, let me write here B and AI. For part I, let me remove B and A. I want to do it for part A, for part I. So copper, as we talked about it, copper will loses electron and oxidizes because it is the electrode potential is more negative here, or it is upper in this table, and chlorine will gain electron. So chlorine will gain electron and reduces. Okay, so because these two electrons will cancel out if we add these two. Of course, the first half reaction is called oxidation half reaction, and the second one is called reduction half reaction. Okay, totally if we add them together, we'll have copper plus Cl2 gives copper 2 plus 2 chloride. Okay, and then so we said copper is, for example, if it is a voltaic cell, this is the vessel of anode, this is the vessel of cathode. We have a galvanometer here which is very sensitive to current, and it shows the current. Okay, so this will be the anode because anions are present here, and this is the cathode because cations are present here. So of course anode in here is copper, and cathode in this pair is chlorine. Okay, so how to calculate the E naught of cell? E naught of cell is calculated like this: E naught of cathode minus E naught of anode. Or the only thing that matters in calculation of E naught of cell is the difference in potential, but the difference must be something positive. The differential of the potential difference of a cell cannot be some negative number. So we need to calculate this difference. So in this formula, cathode is this one and anode is this one. So 1.36 minus 0.34, 1.36 minus 0.34 will be 1.02 volts. So we answer the question in part A, that what is the standard cell potential or E naught of cell in this pairing. Okay, so the standard cell potential is 1.02 volts, and of course these are half reactions, and this is the overall reaction. Okay, in other questions it's more the same thing. Let's do another part of this book. In chapter 23, section 5, it is about prediction for from electric potential. Okay, here in this section we want to be focused on if some reactions takes place or not. For example, we know that zinc, let me talk about magnesium. Magnesium is more willing to lose electron. Okay, and copper is less willing to lose electron. So we know that, okay, in this table 1, copper is here, magnesium is here. Magnesium is at the top, which is very reactive, which is very much willing to lose electron, and copper is less willing to lose electron in comparison with magnesium, of course. We compare the pairs in electrochemistry. So now, if we want to consider this single substitution reaction, for example, magnesium plus Cu2 plus gives magnesium 2 plus copper, and if the question says, does this reaction take place? We say yes, this reaction takes place, because magnesium is willing to lose electron to give it to copper, and copper, in comparison with magnesium, is willing to gain electron and be reduced. And therefore, this reaction takes place, and vice versa will not. Vice versa will not, which means if we have copper and magnesium 2 plus, this reaction doesn't take place. Okay, so prediction of reactions like this is the topic of section 23.5. So it is again a matter of comparison of species in the electrochemistry in a standard reduction potential table. Okay, and it is much the same as reactivity series. For example, if we refer to table 1 once again, let me write here that these are single substitution reaction. Single substitution reactions. Okay, we know that generally metal plus acid will give salt plus hydrogen. For example, if we have magnesium plus hydrochloric acid, it will give magnesium chloride plus hydrogen. And if we want to balance it, we need to put a coefficient of 2 here, and all the others are 1. So it needed balancing. Okay, now if we make them because hydrogen chloride or hydrochloric acid is in an aqueous solution, so it will be it is completely ionizable. And if we consider the ionic form of this equation, the net ionic equation will be like this: magnesium plus 2H plus gives magnesium 2 plus hydrogen. This is the net ionic equation. And of course, chlorine is the spectator ion. So chlorine Cl minus will be cancelled from both sides. So the net ionic, what does this net ionic equation tell us? Let's go back to the table. Here, magnesium and hydrogen. If we compare these two, we say that, okay, magnesium in the presence of hydrogen can be oxidized. Yes. But if we consider copper in the presence of hydrogen cannot be oxidized. So, for example, if we consider this equation is not generally true for all metals. So,